Let us consider this meter scale, or we would like to call it as millimeter. Millimeter. These are millimeter marks, and this is centimeter. Centimeter. And these are millimeter mark, where this is the routine scale or normal meter scale. Now, if I need to measure some length, say from this point to say this point, I can say from here to here. So this distance is 3.4 centimeter. We can say that this can measure up to 0.1 centimeter. So the least count of this ruler will be 0.1 centimeter. However, in this measurement we have two numbers, 3.4. So there are two significant numbers, and in which 3 is very accurate, but 0.4 we are not very sure. There is a possibility of some error in that. So let me define significant figures. Significant figures. Well, in a measured quantity, significant figures are the digits which are absolutely correct. So I can write absolutely correct digit plus, or digits, plus first uncertain digit. First uncertain digit. Let me explain this. Suppose I measure something like this, 125.36, and here these and these 125.3 is accurate. These are the correct digits, and this number, the 6, is the first uncertain digit. So basically this contains 1, 2, 3, 4 and 5 significant figures. 5 significant figures or numbers, and here 4 are correct and 1 is uncertain. Let's have another example here. Suppose there is a number 6.024. Then how many significant figures are there? Well, again I can say 1, 2, 3 and 4. There are 4 significant figures. Let me take another example. Suppose I have some measurement like this, 6.300 centimeter. Now once I write centimeter and trailing zeros after decimal places are significant, so I have to say that there are 4 significant figures in this example also. You got to be careful. Now let me give one more example. Suppose there is a power here, say 1.3 into 10 raised to the power minus 7. So it has only 2 significant figures. Only 2 significant figures here, 1 and 3. Similarly, if I have another number, let's go here, and say this is 0.0032. So this has actually two significant figures only, this one and this one. So if a measurement is less than 1 in this case, and then all zeros count occurring to the left of last non-zero digits are not significant. So these digits are not significant because these digits are left of this one. These digits are left of this non-digit number. This is the first non-digit number. Now also let me give some more example. Suppose there is a change in the unit. Let me just use this color. Suppose there is change in unit. So what happens in case of change in unit? Suppose if I am saying 7.3 centimeter, but we know it very well, it can be written as 0.072 meter, or it can be written as 0.0000. Okay, this is 73, so 0.0000, how many 0? 40, and 7, and then again 3 kilometer. And I can also write as 7.3 into 10 raised to the power 7 nanometer. Well, the unit is not significant. All the cases you have only two significant figures. Now let's study another rule. Suppose the number is 26300 centimeter or 263 meter or 264,000 millimeter. Now what will be the significant figure? All these figures have only three significant figures. So basically all the trailing zeros are insignificant here. Also please note down a term that the exact measurement have infinite number of significant figures. All right, so what does it mean? Suppose 10 apples, or we can say speed of light in vacuum, speed of light in vacuum. These are exact measurement, so they have infinite number of significant figures. Now let me talk about rounding of some digit. So let's talk about rule number 1. Suppose there is a number lying to the right of cutoff digit is less than 5, then cutoff digit is retained as such. Say x is equal to 6.14. So if I have to round it off, I can round off like this: x is equal to 6.1 for two significant figure. And suppose another number is x is equal to 5.328. I can round off like this: x is equal to 5.3 and 3 if I need to round off to three significant figures. Now let me explain about rule number 2. Suppose the digit to be dropped is 5 followed by digits other than 0, then preceding digit is increased by 1. Suppose x is equal to 14.252 and I need to round off to 3 significant figures. So there are 3 significant figures. So I can round off to 14.3. However, let me talk about another rule. If the digit to be dropped is simply 5 or followed by 5, then it will depend like this. Suppose x is equal to 6.250. So x will become 6.25 only. Or no, if it is 6.250, then x will be 6.25 in 3 figure notation or 3 significant figure. Then rounding off will be 6.2. Why? Because before this 5, this is even number. And in case there is even number, we do not change this if this is 5. Alright, number 4. But however, if it is x is equal to 6.350, then x will be 6.4 because here 3 is odd number. Then we will increase this by 1. So let me repeat again here this rule number 4, that if the digit to be dropped is 5 or followed by 5 or 5 followed by 0, then preceding digit is raised by 1 if it is odd.